Hello, welcome to Fluid Mechanics videos. Uh, in this video, I'm going to um, explain how to solve problem 351. It's a moving boundary problem. As you can see that the flow is going to moving control volume problem. So the fluid jet hits it's a vane of or the bucket of a turbine, and turbine rotates at omega angular velocity, and jet comes from left to right. And the first thing here is to find the power delivered to this wheel. So we need to find the power. Let's take power is P, and the power we can find power is equal to the radius is given r, so we can find the power is equal to the torque times omega. So we can find the torque power is equal to torque T times omega. To find the torque T, we need the force applied on the bucket. Force applies on the bucket. The force apply on the bucket times the radius. To find the force, we need to find the force acts on the bucket due to the water strike on the bucket, right? So we need to find the force acts on the bucket. So we know that there's a force acting on the bucket towards this side F, and same and opposite force acting on the fluid. So now first thing is how do we find force? The force is given by sigma F from the linear momentum equation, d over dt control volume rho v dv plus control surface rho v vr dot in dA. So that's our integral linear momentum equation. The first thing is to find the control volume. So the control volume, I will take a control volume that is moving with the bucket in that place, right? So this fluid volume, so if I take it out, you would see a control volume like this. Fluid comes from this side, enters here and leaves here, and there is Fx force apply on that. But this at this very moment, this control volume moves towards this side because this turbine spins. So what is the linear velocity at this instant? The linear velocity is given by v equals r omega. So this is the v of, let's say it's a v linear velocity of the turbine vt, or control volume, right? That's the velocity of the control volume which is moving. So we can make some assumptions. One is the flow is incompressible, and it is a steady flow, and it's non-deforming control volume. since it is steady and incompressible, we can say this first term of the equation 1, first term of the equation 1, first term of the right hand side of the equation 1 is going to be 0. So your our f is going to equal to cs rho v vr dot n. Now and dA. So now we need to identify what this each v means. So this v is right here. This one is the velocity of the fluid with respect to Earth. Okay, and this is the velocity of the fluid with respect to control volume. So now control volume is moving. Okay, so let's identify. Now this is my cross section 1 and cross section 2. So all these cross sections we need to identify what this each velocity is. So for now we'll see that this v2 is, let's take this v2 is the velocity at 2 with respect to the turbine, right? With respect to turbine or control volume, right? With respect to turbine, with respect to the control volume or control volume, the same. In this case, you can say the control volume is moving at the turbine, at the speed of the turbine. So that's what we get in here. That's equal to v2, but it's into this direction. So direction is important. And then velocity of the at 1 with respect to Earth is equal to the jet velocity, because jet velocity is given with respect to Earth, Vj, which is into this direction. And we also know that velocity of the turbine with respect to Earth, which is equal to Vt, which is also equal to r omega, which is also into this direction. Now let's apply this equation, right? Our simplified version of equation. Force, we're going to apply the equation into from left to right. In this case, from left to right. So we have negative f of x equal to at their velocity with respect to Earth is cs vj, and vr is the velocity of the at this point with respect to the cart, right? With respect to the turbine. So to find that, so velocity at 1 with respect to the turbine, it is equal to velocity of at 1 with respect to the Earth plus velocity of Earth with respect to the turbine. So we know that velocity at 1 with respect to Earth is Vj into that direction, and velocity of Earth with respect to the turbine is the negative of velocity of turbine with respect to Earth. That means Vt into this side, so plus Vt into this side. So if you need V1 of t into the right to left, that is, so left to right, Vj minus Vt, left to right, this velocity, this side velocity, because we apply that equation to that side. So now we look at the dot product. This velocity, the relative velocity is into left to right, and n here at state 1 at boundary 1 is into that direction. So velocity in the other direction is into that direction, so it's going to be negative. So we can write negative Vj minus Vt, right? That's, and then have dA. There's a rho in here, right? Rho can be taken out, incompressible. And plus you go to the second one, this is the first one. Rho Vj, velocity of the fluid with respect to Earth. So that's not V2, because V2 is velocity at 2 with respect to turbine. So we need to find velocity of at 2 with respect to Earth. To find that, we can use the same equation that we used here. V2 with respect to Earth is equal to V2 with respect to turbine plus V turbine with respect to Earth. So in this case, this component is V2 into this side. So we can write, now we are writing the equation from left to right. So we can put, this is V2 into right to left plus V turbine Earth is into left to right. So it's V turbine into this side, right? And then this is going to be Vt minus V2. So we can write, this is Vt minus V2 into this, into left to right, towards left to right. And then velocity of 2 with respect to turbine, with respect to the control volume, is V2. So we can write V2 is into this direction, out from that. So V2 times n is V2, and you have dA. So we can take rho out, and from here it's gonna be Vj times, you know, negative sign up, Vj times Vj minus Vt, okay, and dA integral is Aj plus rho Vt times V2 times V2, Vt minus V2 times V2 Aj. Okay, now that's going to be negative fx. So I will name this my equation 2. The problem is that I don't know what V2 is. To find V2, we need to use mass conservation. We need to use mass conservation. So to use mass conservation for this incompressible, steady flow with a moving control volume, we can use integral Vr dot n dA. Now this is with respect to velocity, is with respect to control volume. So yes, so the first cross section one, we have velocity with respect to control volume. For the first control volume, it's going to be Vj minus Vt, Vj minus Vt into left to right, and this is negative, so you put negative, right, dA plus Now velocity with respect to the turbine with the control volume is V2 dot n is positive, dA equals 0. So from this we can get dA is AJ, so dA is equal to so each other, so we can write negative VJ VT AJ plus V2 times AJ equals 0. AJ cancels out, so you can find V2 equals to VJ minus VT. From 3 to 2, we can write negative fx equal to negative rho VJ VJ minus VT AJ plus rho VT minus, instead of V2 I put VJ plus VT, and then instead of V2 I can again put VJ minus VT, and also we have AJ, right? I can put that one again, rho AJ in front of that. So we have here VT, sorry, I need to figure out, okay, VT minus V2 is VJ minus VT, that's going to be plus VT, and VJ minus VT. So you can write, you can take do fx, you can take negative rho AJ VJ minus VT as a common factor. From the first term we have VJ here, and second term negative, because I put the negative sign up here. I should have negative VT minus VJ plus VT, and then you get to have negative fx. I can multiply both sides by negative sign, so I can remove negative sign. Rho AJ VJ minus VT, and then from here I have this is going to be positive twice VJ minus 2 times VT, and I can take 2 out. We have f of x 2 rho AJ VJ minus VT squared. So that's our fx value. To find power, we obtain that P is equal to torque times omega. So here actually I should have actually written that VT in terms of given values. So VT is fx equal 2 rho AJ VJ minus VT is r omega squared, and then also P is equal to torque is fx times r times power is omega, right? And then you have 2 times rho r omega, 2 times rho r omega AJ VJ minus r omega squared. That's the power. So that's your power. That's the power. Okay. So the second question, what angular velocity is the maximum power delivered at? So Now in this case, to find that, we need to find dp over d omega. So if I find dp over d omega, others turns it to be constants. 2 rho r aj, and I'm going to take this part now, vj minus r omega, and then this omega is going to be d omega over d omega over d omega is equal to 1 plus I take 2 rho r, take omega out, a j, and then if you differentiate this one, this is twice vj minus r omega, and then if you do integrate this term, it's going to be negative r. Okay, so we have here all of these 2 rho r aj vj minus r omega is common factor. So first term 1, and then it's going to be negative. You have all these should be gone except omega. It's at omega, and you have omega, and then you have r, and then you have 2 r omega. You have rho, yeah, I checked this right, and then 2 r aj omega left in here, 2 left in here, and negative r in here, so you get negative side. All right, so this is dp over d omega at maximum p. dp over d omega goes to 0, so we can write everything goes to 0. Let me see, can get this one. Rho r aj vj, just to make sure everything is correct. Just to make sure everything is correct. You got 2 dp over d omega, so you write first term, you can take, oh, this should be squared, that's why it should be squared, and then when I get this term should be changed, this term should be changed. So you have vj minus r omega, then you have minus 2 times r omega, 2 times r omega, yes. So now it'll be different. So dp over d omega is equal to 2 rho r aj vj minus r omega, and then you have vj minus 3 r omega. Okay, and now if for maximum p, you're gonna get dp 0. That happens in vj omega times vj minus 3r omega equals 0. It could be r omega equals Vj, or R omega equals Vj over 3. Now when you see when Vj equals R omega, when Vj equals R omega, P is 0. So it could be maximum. So this would be the value that we need to select. Therefore, dp, therefore P is max when R omega is equal Vj over 3, right? When R omega equal Vj over 3. So you can say P max is equal to 2 rho R omega Aj. Now instead of Vj, we can put instead of Vj, instead of R omega, we can put Vj over 3 squared. So we can write 2 rho R omega Aj. This is 2/3. 2/3 squared is 4/9 Vj squared. So we can write this is going to be so nice. Is it Vj squared right? I'm just checking my answers. This is 2/3, so 4/9. 4/9 Vj. Okay, so we have, yep. And also this R omega, instead of this R omega, we can put 1/3 Vj. So we can have 2 rho, instead of this R omega, you can put Vj over 3 Aj Vj squared, right? So you can put 2 times 4 is 8, 9 times 3 27, and then you have Vj cube Aj. So that's the power, maximum power obtained in this instant. So how many then this last one, how would your analysis differ if there were many buckets on the wheel, so that the jet was continually striking at least one bucket? So if the jet is continually striking, the available mass flow rate will be different than the available mass flow rate in the other instant, in the previous instant. So if the jet is continually striking, we can say that power is equal to the mass flow rate would be rho Aj Vj. So we can write 2 times rho Aj Vj, and the velocity is change is r times Vj minus r omega. So that's your power requirement. So in the maximum power, if you want to find the maximum power in this case, rho aj vj, actually I'm missing omega here, omega, in the, I can find dp over d omega. In this case you can get 2 rho aj r 2 rho aj r vj, vj minus r omega plus 2 rho aj plus 2 rho aj vj r omega 0 minus r. So this is 2 times rho aj r vj taken out, and then you have vj minus r omega plus 2 times aj r vj, 2 times aj r vj, you have omega, actually minus omega r, minus omega r. So we have 2 times rho aj r vj, vj minus 2r omega dp over d omega, right? So for max p, dp over d omega should be 0. So you get r omega equals vj over 2. So r omega is vj 2. So p max in this case 2 rho aj, instead of r omega I can put vj over 2, and here vj minus vj over 2. So you can write 2 cancel 2, and then you get rho aj rho aj so here are we missing something? So aj is here, do rho aj instead of, oh, there's another aj I'm missing here, vj. So this vj was missing here, this one. So you can write this is vj, vj rho aj vj squared vj cube 2 divided by vj cube p max. So that's the maximum power obtained in that case. Okay, so that's the answer. So the key is to identify these velocities here, relative velocities, which is the key, and to note that this velocity is with respect to the control volume and this velocity is with respect to the earth. Okay, so that's all. Thank you for watching.